Before delving into the new content, let's take a few minutes to review what we've learned already. So the first question here is very similar to one you may see on an exam. It gives a hypothetical situation, a specific research question has been posed, and then we just need to come up with the correct analysis and what needs to be done. So let's say that a researcher wants to know the proportion of unique variance in some outcome that is explained by an intervention. And furthermore, she has 3 control variables. So what analysis should she run, and what information should be paid attention to in the output? So for this one, it sounds like a hierarchical regression is necessary because the words that should tip us off to that is proportion of unique variance. So the proportion of total variance in the DV, we want to parse that out to the different predictors. And since there are 3 control variables, it seems like, and then one focal predictor that she's interested in, which is the intervention, we are going to think about 2 blocks. The first block is going to contain those 3 covariates, and then the second block will contain the 1 predictor, and that's the intervention. And in the output, she is going to, well, first she's going to ask SPSS for the change in R-squared information, and then in the output in the model summary table, for model 2 or block 2, she's going to look at the change in R-squared, or the bump that intervention gives to the R-squared, and then she'll look at the F significance in the far right column, and that will tell her if that R-squared change is significant. She will be reporting that in her whatever she's doing, like writing it up for publication or presentation, and she will probably also include the B weights because a lot of folks want to know those as well. And so she'll have a regression table that she'll report with all of the B weights, the T and their significance, so the significance of the B weights, and then she will add that this intervention explains an additional X% of the variance in the DV above and beyond those covariates. The second question is another typical one that you might see on an exam, where we have a hypothetical situation, these certain events have occurred, and so you as the researcher need to kind of explain what's going on in this case. So imagine that you analyze a data set with 25 predictors and a total of 37 cases. Typically this again will be someone who wants you to tell them which ones are the most predictive of the DV of interest. So let's say you observe an R-squared of 0.81, and you are excited to report this to the client because it appears that you're explaining a huge portion of the variance, like 81%, so that's really exciting. However, this R-squared isn't significant, so it's very large but not significant. What is going on? Well, what is going on is that we have our N is approaching our K. I'm sorry, K is approaching our N. And so that means that we have this many predictors, and that is almost equaling our number of cases actually in this case. So we have 25 predictors, 37 cases, so we would expect R-squared to be artificially inflated and thus not to be trusted. So the observed R-squared of 0.81 is not to be trusted. So what do you do in a case like this? Well, there are a couple of things you can do. First, you can check the adjusted R-squared and see how low it goes from the observed. And you can report this to the client. You could also look at which variables are very redundant with one another, so you can do a bivariate analysis of all the predictors with one another. And if some are correlated 0.8 with each other, you could set a cutoff. 0.8 and above, we're going to kick one of them out. Depending on your theory, of course, and what's going on with those variables, you wouldn't want to just eliminate them randomly, of course, but think about what they mean and how they may be contributing to the DV, and then eliminate some that way. You could also do a data reduction technique where you put all of these predictors into an exploratory factor analysis, where you, and what that technique does is it helps us understand which ones are coalescing together, which ones are correlating very highly with each other, and you can reduce the 25 into maybe 4 or 5 factors, and then you would combine those predictors into like one variable. So you would find out like a concept that unites them. So some of them may be job characteristics, for example. And so there are different questions on a survey, let's say, and some of them group into what seems like autonomy characteristics. So questions like, my job lets me determine my own schedule, my job lets me, you know, manage my time on my own. My job gives me the freedom to do certain things. And then some questions may be more on the creativity side. So my job involves me coming up with creative solutions. My job involves me thinking outside the box, etc. So an exploratory factor analysis takes all of these predictors and puts them kind of into categories that you name. And then you can use those categories, hopefully a much smaller number, so maybe 4 to 5, 3 to 5, something like that, and then you would use those factors as predictors instead of the 25. And that way you would have 3 to 5 predictors with 37 cases, which is a little bit better. Recall our rule of thumb though, and that is that we want 15 to 30 cases per predictor. So even 5 with 37 may be cutting it a little bit close. But anyway, you get the point. The point is that the N-to-K ratio needs to be appropriate in order to do the analysis. And again, if it's not, the adjusted R-squared and the observed R-squared will be very far apart, and the observed one is not to be trusted in that case. Finally, what is the formula for the t-test for the beta? The t-test for the beta is beta itself over the standard error of beta. And the factors that influence this, of course, we would want the numerator to be very large, or the beta to be large, and we want the standard error to be small. And things that make that beta large is low multicollinearity and a strong bivariate correlation, so that R, the correlation, just the basic correlation with that predictor and with the outcome. Then for the standard error, we want that to be small, and what makes that small is low multicollinearity, and that's about all you need to know for that formula. Okay, so as we go through, keep thinking about these formulas and what happens when we change one aspect of them. What happens to the overall t-test? Does this increase the probability of finding significance or decrease?